Thank you so much for being here. It's great to see this many people in person. And with that, I would like to just go right ahead and introduce Carol Burns, who will give us some opening remarks.
Well, welcome everybody to the 5th Annual Berkeley Lab Research SLAM. Let's hear it. It's so good to see everybody in person, and this is certainly a great event to round out this year's National Postdoc Appreciation Week. So welcome. This is going to be our first in-person SLAM in 3 years, and the very first one to be outdoors in our beautiful weather. Awesome. So we're thrilled to be able to come together to celebrate in person this year, and that we can also connect with our virtual community that are streaming in from all over the world. And I think that's our, yesterday I focused the wrong direction. I think that's our camera. So hi world, welcome to SLAM. So I know there's gonna be recognitions later, but I certainly wanted to start by thanking all those who are responsible for creating this fabulous event. So starting with the Career Pathways Office, Meg Rodriguez, Justin Placentia, and Stephanie Harding, who ideate, who create, who manage, and who execute the overall program in the process. So let's hear it for those guys. And of course, it takes a village, so I certainly want to acknowledge the involvement of strategic communications, creative services, our awesome AV and audio folks, as well as all of the lab photographers and everybody who helps out. Thanks to everybody who served as screening judges and those who served as communications coaches. And finally, big thanks to our MCs, Sinead and Bashir. So thanks very much. So what's great about the SLAM is it gives us a chance to really meet some of our postdocs and early career scientists and to hear about their research. Today, we're going to hear from 12 postdocs who have been challenged to summarize their research in just 3 minutes or less in a way that is understandable to a non-specialist audience. This is a really hard thing to do, and these early career scientists have worked hard to get here. Mastering this type of communication is going to enable these speakers to connect with other scientists, both within and outside their field, and with the public. It's important now more than ever that scientists be able to communicate their got it? Okay, that these scientists be able to communicate their research to a broad audience. While this event is fun and engaging, it helps to build critical skills that these researchers will take with them as they progress in their careers. Science communication is absolutely necessary to advance Berkeley Lab's mission and allows us to describe research accomplishments to our sponsors, of course, to attract and engage partners and collaborators from across science domains, to demonstrate our value to state, local, and federal lawmakers and stakeholders, and to connect with the broader communities in which we live. So it's my pleasure to introduce to you the inaugural Berkeley Lab Research SLAM to this first outdoor one. Our theoretical material scientist and staff scientist at the Molecular Foundry. You may also recognize her as this is her 4th time co-hosting this event. Please welcome me and please join me in welcoming Sinead Griffin. Let's hear it for Sinead. Give it up.
Good morning, good afternoon, Berkeley. Okay, okay, we're getting there. Okay, so it's me again, surprise. You probably noticed, though, I'm on my own this year. Unfortunately, David Gilbert, our longtime host and co-MC, has retired. So we had to do a pretty thorough search to find my new MC squared. MC squared. Come on, folks. We got 2 hours of this. And by the way, this is going to be my last year doing the SLAM presenting. So all of my worst jokes are coming out over the next 2 hours. Okay, so do you want to hear about who my next MC squared is for the next 2 hours? There we go. There's some enthusiasm. Okay. So coming all the way from Nigeria via Leeds in England and the computing sciences area, we have Dr. OMG himself, Dr. Bashir Mohammed from the computing sciences area. Come on up here, Bashir, and join me.
Testing, testing. Thank you very much, Sinead, for that beautiful introduction, and thanks for the nomination. I'm super duper excited to be here today. By the way, aside being a scientist, I'm also an aspiring stand-up comedian. Is that funny? Okay, so I'm gonna get you to do my catchphrase, which is OMG. Do you know what that means? Okay, so once I throw my hands in the air, I want the folks here to say O, and on the right-hand side, I want you guys to say M, and everyone is gonna say G. Are we ready? Okay. O, G. One more time. G. Thank you very much. Thank you very much. It's such a thrill to be here today, honestly. So by the way, I joined the lab 3 years ago as a postdoc. I moved down from England to the United States. And I've never, ever been to the US before. I only know 3 things about the US. Number 1, Hollywood. Number 2, Los Angeles. Number 3, Sinead, do you want to take a guess? Wrong. She said Berkeley Lab. Number 3 is Kim Kardashian's. Was that funny? Thank you very much.
So maybe we should go on with the show then. Right, so it is going to be a live show, and as you've probably seen already, some things will go wrong, but we hope that most of it goes right. But to give you a bit of insight into what's going to happen today, Bashir is going to give you an overview of what you're going to expect over the next hour and a half.
Okay. Change it. Okay. For today's event, please, the first rule, don't worry, I have it in my head. So the first is please silence your phone. You're only allowed to use your phone if you want to go on social media and tweet. Aside that, you're not allowed. Or if you want to go on Instagram. Are we on Instagram? I'm not sure. Yes, Berkeley Lab is not on Instagram. So 12 amazing finalists will be competing today. 3-minute stories and also 1 entry song per contestant. Our beautiful timekeeper will signal our speaker when the time is up. In between each finalist presentation, it will be your turn, to participate. Please join in the trivia contest. You know why? There will be lavish prizes. So in the end, we'll also give you, the audience, you have the opportunity to vote for your favorite finalist. Following this, the judges will deliberate and make their selections. And make sure you stick around because the winner is going to be announced at 4:50, I think, approximately.
How about that?
Yes. So, next slide. These are our social media links. Please, here are the details of our hashtags and handles. Please remember, only use your phone if you want to do social media. Please remember to tag us, in your tweets. That's very important. Over to you, Sinead.
Okay, so it is Berkeley Lab, so it's all about team science, but we're going to have a winner today. And it will be a competition between all of the areas. So I'm going to actually get everyone to shout out for whichever area you're in now. So is anyone here from computing sciences? Woo, computing sciences. Okay, next up, earth and environmental. Ooh, not as enthusiastic there, I guess. Physical sciences. Ooh, let's get physical. Okay, energy technologies. Okay, bio. Bio is always strong. And energy sciences. Go energy sciences. Ooh, I'm not biased, but I hope energy sciences wins. Okay, so there are prizes today. Not only do they get a really big check if they win, they also get the money associated with the check. So our first prize winner is $3,000, second prize $2,000, third prize is $1,000. And the very important prize that you will all play a big role in is choosing the People's Choice Award. Yeah. So right after everyone has already given their talks, you can't do it until you hear everyone. Obviously, you're not just going to vote for your own area. Then you will have a chance to vote. So you can see that everyone has one of their little brochures. And on the back of the brochure, there is your voting slip. Those of you watching online, there will be a link in the chat that you can also vote online for your favorite person. Okay. The poll will only be open for 10 minutes, so make sure you do get your vote in right at the end before you go and have some refreshments and snacks at the end. Okay, so then we will go through the judging criteria. So we will be judging the esteemed judging panel will be judging our contestants on several things, ranging from the technical content of their talk to their clarity at presenting it, and also their stage presence and enthusiasm at presenting their work in just 3 minutes. They will also be docked marks if they go over 3 minutes, so that's why we have our timekeeper right on hand.
Yes.
So Bashir, do you want to tell us who has the hard job of deciding?
Yes, absolutely. So we're very grateful for our distinguished panel of judges for the 2022 Berkeley Lab Research SLAM. Ladies and gentlemen, permit me to introduce our 5 esteemed judges. First, we have Berkeley Mayor Jesse Aragon.
No.
Okay, no. We have Jennifer Tang, Director of Communications Relations. Berkeley Lab, yes.
Woo.
A round of applause for Jennifer, please. Then, second, we have our own Carol Bonds, who is the Deputy Director of Research and Chief Research Officer at Berkeley Lab. A round of applause for her, please. Next, we have Sophia Chen. Sophia Chen is a freelance science writer. A round of applause for her, please. Then we have Cecilia Fura. Cecilia Fura is a Senior Manager of the Visiting Scholar and Postdoc Affairs, VSPA for short. Round of applause for her, please. Am I missing anyone?
That's it, I think.
That's it. Please, can I ask the judges? One more, yeah. So, and we have Supervisor Keith Carlson, who is a member of the Alameda County Board of Supervisors. A round of applause, please. Yes. Please, can I ask our judges to stand up and wave their hands for recognition? Now you know who to bribe.
All right, so they say everyone is king for a day, but everyone is a champion here once they take part in the slam. So we have several of our former slammers in the audience. So do you all want to stand up and give everyone a wave? Former slammers, so wave. There we go. And it's warm, so it's okay. You can take off the slam hoodies now. You've done your job. Thank you. Thank you for putting up with it. Okay, I think that's us. I think that's us ready to go.
Now, let's get the 2022 Berkeley Lab Research SLAM started. Round of applause. First up, all the way from the mighty biosciences area and the Joint Genome Institute, please, ladies and gentlemen, give it up for L. Bonds.
You're sitting at home, scrolling through your phone, when up pops a notification from your favorite social media app. You have a new suggested friend. But wait, how did this social media app know to suggest this friend to you? The answer? Networks. It's all about who you know, who your friends know, and so on. The truth is that networks have been used by scientists for decades for understanding social ties, traffic patterns, and brain chemistry. Well, it's even true for microbiomes, the collection of microorganisms, bacteria, fungi, viruses that live in, on, and around us. For example, scientists estimate that soils contain 1 billion microorganisms per gram, which could represent millions of species, and within these webs of diversity could be trillions of interactions. But why should you care about these microscopic social networks? Well, it turns out that these relationships aren't tied to how a microbiome functions. At Berkeley Lab, we're interested in understanding the links between plants and their microbiome, as well as between microbes within the microbiome. And this is because plants just like us, form symbiotic relationships with microbes to help them grow better, especially under extreme environmental stress like drought. But how do you survey a microbiome? With its DNA, of course. It tells you who's there, in what abundance, and with whom else. And so for a while, we knew that stress could change the diversity of microbes that plants associate with. With network science, I was able to discover that it also completely reorganizes the network. In fact, it changes not only who associates with whom, but also who serves as hubs, which you could think of as the social butterflies, the most highly connected taxa that serve as keystones in the network. I also found that these microbes become more connected, especially among taxa believed to help plants grow better. And most surprising, while we thought that stress would increase competition for resources, we actually found that it might promote cooperation and aid in microbiome stability over time. So, this is only just the beginning, because each microbe in the network has its own story to tell and its own genome filled with information to uncover. The next frontier, linking these relationships to their genomic and metabolomic mechanisms. With this, we'd be able to better suggest microbes to use in biofertilizers that could help plants grow under a rapidly changing climate. With this, we might even call it Facebook of the field.
Okay, folks, it's trivia time. Do you remember this from last year's? It's your time to show how nerdy you are about Berkeley Lab. Okay, right. Question 1. In what center was a second beamline created for the petawatt laser? Okay, so I don't see any hands. Okay, I'm going to...
Anyone?
Okay,
I've
there's a
got
few
the mic
hands.
here.
Is the Bella Center?
It is Bella.
Round of applause, round of applause.
Bella. Any Italians here?
Gifts.
It's the
Where is it?
beautiful center. Yeah, there's a gift for you there somewhere. No, well, there. Okay, I'll tell a joke while we're waiting for the gift. So, you know, there's loads of goats, our Berkeley Lab goats. Do you know what they eat for breakfast? Goat meal. Okay, next. Then we have all the way, coming all the way from the computing sciences area, we have Jean-Luc Bez.
Do you recall that children's puzzle called Where's Wally or Where's Waldo? The one where we have to find a character dressed in red and white stripes and blue pants? You know how hard it can be to find him, right? That's because there is a lot going on in the picture, and the same goes for a supercomputer, when multiple scientific applications are running. Scientists rely on such machines to understand the world that we live in, from atoms to stars. Those experiments can run for hours, days, or even weeks, and they generate a massive amount of data, quite often not in an efficient way. For instance, a regional scale earthquake simulation can generate 75 terabytes of data in a single experiment. That's roughly the same amount of data you transfer while watching Netflix in 4K resolutions for over 1.5 years. So now you understand how big of a problem we're talking about here. And making sure we're moving data around in the system in an efficient way, it's a very tricky problem. Moreover, because of the complexity of today's supercomputers, when things start to go slow, it's much harder to find the problems than finding Waldo in the puzzle. Here at Berkeley Labs, in the Scientific Data Division, we're working towards enabling faster science, so scientists can get the data they need as fast as possible without having to worry about bottlenecks. The way that we do that in our research is by using metrics that are collected on the system, which comprises different aspects of its complexity. And we apply different techniques, from statistical analysis to data mining and machine learning, in order to detect patterns and the root causes of those performance problems. So then we can map into solutions and applications can run faster. You can think of it as having a much clever way of finding Waldo, instead of just randomly looking at the picture, hoping to find him. Because we're working at the system level, we also get a unique opportunity to interact with distinct science domains, and different applications can use our solutions. For instance, a regional astrophysics application, we managed to get it run 4 times faster, and a linear algebra application 200 times faster. All of this by optimizing data movement in the system, considering the unique characteristics of each application and domain. We do strongly believe that our research can help find and fix those performance problems so scientists can get the data they require and worry about what's the most important thing, the science they do. You can think of it as we're proposing a much more clever, automatic, and faster way of finding Waldo in the puzzle.
The Lux Zeppelin experiment, led by Lawrence Berkeley National Lab, is located where?
So we had someone get it within a microsecond. You better get it right now.
I think I got it right, but this is just a guess. South Dakota?
Is South Dakota the answer?
Close enough, close enough. Yes, I'll give it to you. That's the answer. But it's Stanford Underground Research Facility. Next year. Yes, so I'll give it to you. Audience, is that close enough? Close enough, close enough. Round of applause. Next up, representing the powerful energy sciences area, please, ladies and gentlemen, welcome Gan Chen.
Can you imagine power outage after sunset every day? No TV shows, no internet, and you have to stay in complete darkness. Sounds horrible, right? United States have set the goal to reach 100% renewable electricity by 2035, and at least 50% of which is estimated to come from solar energy. But the sun is not always shining. The solution is that we must generate extra electricity when there is sunshine, temporarily store the electricity, and release it when needed. The most well-established technology for grid-scale energy storage is pumped hydropower. For this system, two water reservoirs at different elevations are needed, one high and one low. This system will store energy as water is pumped to the upper reservoir and release electricity as water flows back to the lower reservoir through turbines that rotate generators. This system has an 80% efficiency, however, wide applications are limited by geographic constraints. My research at Berkeley Lab is to address this need by developing a battery system that pumps electrons instead of water. The two water reservoirs are now replaced with two gigantic tanks filled with liquids. The liquids can carry electrons at different energy levels. So this system stores electricity as the electrons are pumped to the high energy tank and release electricity as the electrons flow back to the low energy tank. During operation, the liquids in the tanks are being pumped to flow through the porous electrodes to enable continuous electron exchange, which is why this system is called flow battery. Flow batteries can deliver energy for over 10 hours and don't require precious metals like lithium or cobalt, which makes them great for grid-scale energy storage. To further improve this technology, now we're filling the tanks with solids that can carry much more electrons within unit volume compared to the liquids. And the solids are now the real electron hosts. The liquids flowing through the solid and the electrodes are just shuttling electrons between them. With such new design, now at least 10 times more energy can be stored within the same tanks. Hopefully, with technologies like this new flow battery that we are working on, we can still enjoy our favorite TV shows after dinner in the new era of carbon-free electricity.
All right, trivia time again. And if anyone was paying attention when I won in 2018, you should know the answer to this one. So, dark matter makes up what percentage of the total mass of matter in the universe?
Anyone? Anyone? That's very simple.
Seriously?
23%.
23%. Is that right?
No, it's not right.
Is that close enough?
No, it's definitely not
Anyone
close.
else?
There's someone over here beside the gifts.
99%?
99%. Oh my God. OMG. Anyone else?
I think I need to improve my science communication skills.
65?
No.
65. Is that close enough?
No.
Anyone else?
50.
Oh my goodness.
I think we're going through all the numbers now.
Yeah.
Okay, we've
Anyone-
got 4 so far. We're going to be here till 5.
I know. Okay.
93?
No.
93. Oh my goodness. Is that close enough, Sinead?
No.
Wrong.
I'm going to start telling jokes again.
Anyone
if we
else?
don't get this right.
2%.
No.
Oh my goodness. Sinead, is any of your postdocs here? Maybe.
No, they're not.
Okay.
80?
Oh my goodness.
What was it?
80.
No. No. Unless it's within 1%, you're not getting it right. Serious? Okay, there's someone at the back. Yeah.
95.
No, we had that one already. Okay, there's like 70 numbers left to go. What? Do we have another person over here?
Yes, we have someone here. Hold on.
Did someone Google it yet?
27.
No. I'm so
Googling is not
disappointed.
allowed. Googling is not allowed.
I'm glad I'm
We're
retired.
going to start throwing out numbers. So 43.
No.
Oh my
No.
goodness.
No one's even against 42 yet.
99.5%.
No.
Oh my goodness. What's going on with this?
97%.
No.
97%.
We've got someone over here who looks like he knows the answer with the hat. You better know it now.
Do you know Sinead? Do you work with her?
75.
No. Okay, there's someone in the back. And if you don't get it right, I'm telling a joke.
85.
85 is
85.
right!
Oh my goodness. Oh my goodness.
You're all saved. Just
Sorry,
about
can you please
saved.
tell us your name, please?
What was that?
Your name, please.
Oh, Tay.
Oh, Terry,
Tay.
yes. He deserves a Nobel Prize, honestly.
Yeah. Champion of the year. Okay. So, representing the physical sciences area where clearly not enough of you come from, is Fatima Garcia.
You know the shape. You may remember from grade school that the columns and the rows are important, and you might recall that there were some empty spots towards the end that still needed to be filled. The periodic table of elements has been hanging in classrooms and chemistry labs all over the world for decades. So what would you do if I were to tell you that its classification system may not be totally right? The table arranges the elements based on their proton number. This is how we define them to be elements. And the columns and the rows arrange them based on their electron configurations. And it is these electrons that give elements their chemical properties. For 150 years, the table has allowed us to predict what new elements we're going to do before we even discovered them, based on their placements. This, however, started breaking down once we began discovering the super heavy elements. These are those elements above number 103, and they're starting to behave in some really strange ways. Oganesson, for example, element 118, and one of the last ones to be officially named, should be the very last noble gas in the group. Theory, though, is predicting that it'll behave more like the elements in the volatile nitrogen group. Copernicium, on the other hand, element 112, and named after Copernicus, is behaving more like that last noble gas. If we follow the numerical ordering, then the chemistry no longer makes any sense. And if we follow the chemistry and the configurations, then things are no longer in order. And this is just one of the many conundrums currently facing the table as it stands, with an international team of scientists trying to figure out what do we do. There's a debate going on. Do we adopt a convention? Maybe the shape itself needs to change. The community has requested for more experiments so that we can find a way forward. However, you can't just take these guys off of the shelf to then get it on the benchtop. First, you have to make them. This is difficult. Usually, we can only make them at the rate of 1 out of a week or 1 out of a month. Then you have to watch the chemistry. But these guys are radioactive, so they will decay away. So you have to do your measurements fast enough. This is exactly what we do in the heavy elements group at Berkeley Lab. We do modern-day alchemy. We take a beam of ions and hit it against a stationary target, making our new heavy element. Once it's made, we can trap it using a series of electric fields, and into this trap, we can inject a series of gases to do chemistry. We can see what the element reacts with and what it doesn't, giving us information about its chemical properties. At the rate of 1 atom a week or 1 atom a month, it'll take us a while, but our experiments will provide the community with the key information needed to settle the great periodic table debate. Maybe one day in the future, the periodic table of elements won't look like a table anymore, and chemistry itself may not be as it was once.
Okay, which experimental particle physicist enabled California's per capita electricity use to remain flat for more than 40 years?
Okay, so, oh, we have someone already, okay. Doo-doo-doo.
Art Rosenfeld.
Is Art Rosenfeld the answer?
Correct! Round of applause. Thank you, thank you, thank you very much for that. Next up, representing the powerful energy sciences area, ladies and gentlemen, I present to you Sabari Ghosh.
What do you think is common between electric cars that many of you drove here today? The cell phone in your pocket and MRI used for medical diagnosis? Well, the answer is rare earth elements, aka the lanthanides, or more importantly, that lower bottom row of elements in the periodic table that often goes unnoticed. These elements are major ingredients in all modern technologies, and hence they are also termed as the vitamins of modern industry. Now, as their name suggests, they are comparatively rare for usage due to various geochemical factors, and geographically their abundance is far from here. So, it is really important to find out ways to reuse and recycle them. But these rare earth elements are like minions. They look alike, they behave alike, they react alike, but they are specific in their applications. So, the major challenge for using these elements is to selectively separate them from each other. And this is where my research comes in. Current industrial separation techniques of these lanthanides involves generation of large amount of hazardous chemical waste along with non-selective separation. So here in Berkeley Lab, we address two major challenges related to the separation of these elements. One, to have environment-friendly separation techniques, and number two, to have optimum selective separation. Now, who does a better job towards selectivity than the proteins in living organisms? The human body is made up of a multitude of proteins, but each one has a very specific functionality. My research focuses on drawing inspiration from the building blocks of these proteins and to engineer them to develop bio-inspired materials, which are known as peptoids, and to use them to bind these near-similar elements. The usage of bio-inspired materials will also help us in addressing our first major challenge of not generating hazardous chemical waste. Furthermore, screening of different materials to get the best selective binding with these elements may take years. So for that, I also aim towards developing a robotic screening approach where we can use different materials to screen these elements in one individual experiment. Exciting, right? And with this, I look forward to minimize the deficit of these vitaminions in our modern industry.
You're not going to get this one right. Okay, I'll try it. A Berkeley Lab team, in collaboration with NREL, the National Renewable Energy Lab, has developed Building Energy Efficiency Data Management Software. What's it called? Okay, we've got someone in the front here.
Let's go.
Am I allowed to guess what someone put in the chat?
Yes.
You're too honest.
Sinead, is she allowed to guess what someone put in the chat?
Yeah, why not? No one else is going to get it right anyway.
City BS?
No, you can't even read it
No.
right.
Oh my goodness. Oh, anyone else?
I'm going to start with jokes again soon.
Yes, I think Ote is raising up his hand, but we don't want another Nobel Prize winner. We want someone else. Yes.
Anyone else?
Anyone?
No?
Oh my goodness, what's going on here?
She had all the letters right. They just weren't in the right order.
All right, okay. Was it close enough?
No.
Close enough. Any
No,
close
not
enough?
close
Any?
enough, no.
You were allowed to guess, actually. Is guessing allowed?
Yeah, well, I don't think they're going to guess it, are they? Yeah, it's a hard
Okay.
question.
Anyone?
Who wrote these questions?
Beams. Beams.
Beams.
Beans. No.
Building.
Oh, she said beams.
No.
Building energy efficiency management.
No.
Is that correct?
No. No.
Oh my God, why are these questions so difficult?
What do physicists miss from every good party?
Yes, that's a clue, right? Okay.
The punchline is the invitation. There we go. There. That's okay.
Okay.
I think we're going to tell them the answer now. Is there
Yes,
anyone
let's give it to
actually, Faith,
one moment.
Is there anyone
Sinead, one
anyone-
moment. We have
One
someone
more
here who
moment.
wants to try.
Seeds?
Seeds is the right answer.
Oh my goodness. Guess what? What's your name again? What's your name?
Kaya.
Kaya is standing next to Ote. You remember our last Nobel Prize winner? I won the difficult question. Yes.
That is a big coincidence.
Exactly.
Really
That's a big
coincidence. Okay. Right. Next up, coming from the energy sciences area, my favorite area, is Sarah Gleeson.
When you were in elementary school, do you remember learning about the 3 main states of matter? There are solids that have a defined shape and volume, gases have neither of these, and you probably learned that liquids have a set volume, but can flow and take the shape of their container. I want to challenge this conventional thinking about liquids and show that defining the shape of water can be harnessed with powerful results. This is an idea that's found everywhere in nature. Take the cells in your body, which are basically tiny liquid compartments that are supported by membranes that give them shape and protection. What if we could design new materials to make membranes that were able to replicate the function of our cells? Imagine an artificial cell containing carefully shaped internal liquid compartments. The cell could move through your body and deliver a number of different therapies just by rearranging its membrane structure, releasing a drug or synthesizing a protein on demand. It's really exciting to think about the future of medicine this way, but one of the biggest challenges to achieving this is that current membrane technologies don't effectively adapt in dynamic environments like your body. What we need is a better understanding of how responsive materials can be used to give shape to water that changes over time. This is where my research comes in. In my work, I design thin layers of molecules called surfactants that form barriers between fluid phases. It's similar to how a water balloon is able to separate water from the surroundings, except for my membranes can be 1,000 times thinner than a human hair, and they're able to lock water into whatever shape I design it to be. In order to achieve those lifelike properties that are so important for artificial cells, I design my molecular barriers to have a specific lifetime. I add high-energy molecules as a chemical fuel, and when that fuel is in place, those balloon-like membranes are also in place. When the fuel tank runs empty, the balloon pops, allowing the liquid inside to reshape and react with its surroundings. By carefully controlling the chemistry, strength, and lifetime of these nanoscale membranes, I'm able to engineer larger-scale liquid systems that evolve over time. So, by reshaping the way that we think about liquids, we're paving the way for future advances in artificial cells and more effective and versatile medical technologies. I think we can all agree that this is one idea that really holds water.
We always want ideas that hold water, right? It's trivia time, people. I think nobody's going to get this. This is so hard. Christopher Nolan is directing a new film about the Manhattan Project called Oppenheimer. Which actor is playing Ernest Lawrence?
The answer is not James Analytis.
Josh Hartnett.
Is it Josh Hartnett? Yes.
Yes. Round of applause for her. That was so great. Next up, all the way from the Earth and Environmental Sciences area, ladies and gentlemen, give it up for Mohammed Ombadi.
Because I'm happy. Clap along if you feel like a room without a roof. Because I'm happy. Clap along if you feel like happiness is the truth.
Have you ever wondered how rainfall makes its way from clouds up in the sky to the fast-flowing rivers of Earth? Well, the slope of the Earth's surface shapes areas that collect rainfall and direct it to a single point in a river. These areas can be as small as a football field and as large as covering half of the United States. We call them hydrologic catchments, and they are precisely what I want to talk to you about today. But before that, let's talk about us, humans. In our lifetimes, we experience a wide range of adversities. We get sick, we face emotional shocks and financial difficulties. And once in a while, we have to deal with the nervousness of presenting in a research SLAM. And whenever we encounter those difficulties, it is always interesting to ask why some of us are better than others at handling those difficulties. Why some of us recover quickly while others don't. Now, hydrologic catchments, as big and massive and different from humans as they also experience adversities. These are in the form of floods, droughts, heat waves, and wildfires. And just like humans, the response of these systems to adversities can be quite distinct. Some catchments bounce back following disturbances, while others might not recover at all. It is puzzling, and unfortunately, we do not fully understand the reasons behind this. Traditionally, environmental scientists used expensive natural experiments or simplified model representations to tackle this question. However, these approaches have their limitations. So here at Berkeley Lab, my team and I utilize recent advances in data science to address this question by learning from observations. In my research, I analyze a wide range of field measurements to try and identify the main factors responsible for the behavior of these systems. By doing so, we are able to help decision makers answer key questions, such as whether to build a dam, add a forest, or deforest a catchment area, how to optimally manage groundwater withdrawal during droughts, and so many other questions. As the global climate continues to change, threatening our freshwater resources, these are the kind of questions that we need to answer in order to make sure that hydrologic catchments always recover following disturbances, to cope with future climate and provide us with fresh water for many, many generations to come.
Another trivia question, folks. What microbes are the evolutionary descendants of the first organisms on Earth capable of converting sunlight, water, and carbon dioxide into sugars and oxygen? Okay.
Anyone?
We got a few at the back.
Cyanobacteria?
Yes. First guess.
Sign
well
correct.
done.
Round of applause. Please give him one of the lavish gifts.
You're getting better at this. I knew if we were really stuck, Nigel's sitting right here in the front, so I was going to start picking on him. Okay. Next up from the energy sciences area, we have Alexander Pattinson.
Have you ever been stuck in your office doing some really long, boring, repetitive task and wondered, why can't the computer just do this for me? Scientists certainly know what that feels like, especially when we're running our experiments. Take my work, for instance. I work with electron microscopes, using high-energy electrons to study the arrangement of atoms in materials. Cool, yes, but taking data from them is a really long, boring, repetitive process. Move, take an image, move, take an image, over and over again. Now, admittedly, moving and taking images are simple operations for computers to handle. The problem comes in deciding where to move and what images to take. Not every bit of a sample is useful, so we want to be selective, focusing only on what's interesting and disregarding the rest. Interesting, however, is often a rather difficult concept to explain to a computer, especially in microscopy. Imagine that you're looking at my hand, for instance, and you want to take images of all similar particles. Well, it's fine if your particle exactly matches your reference image, but what if it's at a different orientation? What if it's smaller or larger? What if one of the fingers is broken off? Ordinarily, each one of these different possibilities would have to be individually programmed when you're designing your program, which is just more trouble than it's worth. That's why us microscopists tend to resign ourselves to doing the long, boring, repetitive task of taking data manually. But fear not, there is a solution. Unlike normal computer programs, artificial neural networks are really good at recognizing images for two reasons. One, unlike normal computer programs, they see objects as collections of features and don't rely on exact matches to reference images. Two, they're a form of machine learning. They teach themselves how to think rather than being told how to think by a programmer. This means that they can dream up brand new algorithms that us humans might never be able to imagine, all without us ever having to write a single line of code. So how do these networks help me with my microscopy? Well, if I provide images of my particle of interest in all its different possible configurations, a neural network can learn how to recognize all these different configurations. Then, when I look at a large area of a sample, my neural network can pinpoint all these particles of interest and instruct the computer to zoom in for a closer look. Once it's done with this area, it can move on to the next area and do the same again, and the next, all without me ever having to be in the room. So there you have it. Neural networks are capable of making intelligent decisions in the heat of an experiment, automating the entire process. And just like that, the long, boring, repetitive task of taking data is a thing of the past.
Thank you very much. Trivia time, people. This looks very easy. How many directors has the lab had since opening its doors in 1931?
Okay, we have one person already.
17.
Is that right?
No.
Okay, we've got lots more numbers to guess, folk. Anyone else? How many Berkeley? Anyone remember 1931? Maybe want to guess? Anyone was here then? No. Okay. It's lower than 17. Okay. You're getting, okay?
13.
13? Is it 13, Bashir? 13?
No.
No,
wrong.
it's not 13. Okay. Yeah.
10.
10.
We're getting close. But the answer is not 11, so don't even go there. Oh my goodness, that's it.
Everyone's going to have to get a tour and a dark matter lesson after this.
Yes.
Okay, anyone else? So it's not 10, 13. I don't know what else was guessed. Yeah.
7.
7. I can name 7.
No.
Okay, anyone else? No? Oh, we've got more over here. Yeah.
I was going to say 9, but someone over there. Yeah.
9.
Very, very close. Wrong. Sorry. 8.
8.
A round of applause for him. Correct. Okay, yeah, just give it to Jane. Yeah, she said 7, right? Yes. Jane, please. Yes. Round of applause for her. That was close. Yes. Okay. Next up, representing the powerful physical sciences area, please, ladies and gentlemen, welcome Emil Rafos.
Did you know that bananas contain radioactive potassium? Now, like many, I love eating bananas. So is this something that we should worry about? As a nuclear physicist who does my research with radiation safety, that's the kind of question we could be asked. if an object or an area is safe. It's not often that we're actually asked to measure fruit because, spoiler alert here, bananas are safe. It turns out that a lot of Earth is just naturally radioactive. Instead, scenarios we look into are like the accidents that happened in Fukushima or Chernobyl. In those cases, it's essential to quickly map radiation so you can minimize the damage. Or we look at lost sources like stolen nuclear material, or if there's a dirty bomb that needs to be found. When we do these searches, you typically take a radiation detector, you move it around, you see not so much here, a little more, a little more. You play this game of hot and cold. And when you play that game with radiation, you want to do it as quick as possible, and you want to minimize the exposure to people as much as possible. To tackle these 2 points, what we do is we hand over the detector to a robot. Could be a robot on wheels, on legs, or flying like a drone. So we have systems that take the radiation detector, they go up in the air, start moving over an area. And what you quickly see then, and this comes back to the bananas, is that they're not the only thing that are radioactive around us. The ground is radioactive. We all are radioactive a little bit. Since I started talking here, we've all had thousands of radiation particles passing through us. And they're nothing to worry about. It's all part of that natural radiation background. But I worry about them a little bit because they end up in our data. When we go out and look for a very weak source, that background radiation can drown the real signal. I write algorithms using machine learning to really squeeze out those last bits of information, the faintest of signals that we have in the data. I also use tools from the robotics world. I add lasers to our robots so they can go in an unknown environment and scan in 3D, create a map and navigate through it, and overlay what radiation there is, how much it is, and they come back and tell us that. And this creates systems that allow us to stay safe and safe and prepared and healthy. So on that note, please continue to enjoy bananas so that you can all stay your healthy, radiant selves.
We get an extra applause because we weren't able to arrange a no-fly zone for the SLAM, so good job to Emil for staying on track for that. So what fruit contains barium and 2 sodiums? Barium and 2, yeah. Bananas.
Bananas.
No, that wasn't trivia, sorry. No, that was another attempt at a joke. Okay, so we've got a who am I? I'm not having an existential crisis. This is the trivia question. Who am I? Okay, I led a Fermilab experiment, was part of the Tevatron Accelerator upgrade, and a research team that designed the Lux Zeppelin project. Who am I? So that's a dark matter project, by the way, folk. Who am I? Seriously?
Seriously? Come on!
OMG.
Who am I? Really? Really?
I think we might have someone at the back.
Yeah, we have someone here. Just hold on 1 minute.
Is it Mike Witherell?
Yes,
Mike Witherell! Round of applause, round of applause, round of applause. Sorry, what's your name, please?
Ariana?
Ariana. A round of applause for her. That's really...
Ariana's getting promoted. Okay, so next up, coming all the way from biosciences, we have Aparajitha Srinivasan.
When was the last time you went to a movie night? Remember enjoying it with some popcorn with a nutty roasted aroma wafting about? There are additives in your popcorn that enhance this aroma and flavor. Where do these additives come from? It can be made using chemical synthesis, but you do not want chemicals ending up on your plate, do you? We can also extract them from natural sources such as plants, but we need tons of these plants to make even 1% of these natural aroma compounds. Certainly not sustainable. That's why I use microbes to make more of these aroma compounds in a sustainable manner by feeding them just plant wastes. Let's get back to your movie night. What if I ask you to drive to the movie theater? what's the first thing that you'll do? Okay, Google, get me on the fastest road to the movie theater. Now, Google will predict the best road out of all possible roads and gives you an estimated time of arrival, or the ETA. Likewise, I use computational models to predict the optimal road, or the pathways inside the microbial cell to get to the maximum possible amount of these natural aroma compounds that I can make. Then I test it out experimentally in the lab. Do you think I'll end up with loads of these aroma compounds on the very first go? Here's a clue. How often do you expect to reach the movie theater at exactly the same time that Google predicted when you first started the journey? Probably not, because there are a lot of factors affecting your ETA, like the conditions of the road, the number of vehicles on the road, regulating traffic signals. Google collects these real-time data and updates your ETA. Likewise, I need to collect real-time updates happening inside the cell in the form of experimental data at multiple levels, such as at the level of the genes, the proteins, and their regulation. I then feed this data back into my model to help it make even better predictions. This model-guided microbial engineering not only enables me to make predictions for making more aroma compounds, but also compounds that can be potentially used as jet fuels. So the next time you're enjoying your movie night with some popcorn, I hope you'll remember me and my microbes on the hunt for the road to natural aroma compounds in a sustainable way.
What is Berkeley Lab's One Lab initiative this year?
It is not to paint all buildings pink. Okay, anyone know what the lab-wide initiative was? Really? Okay, over here. Can you tell?
Zero emission, carbon zero.
Carbon zero emissions? I think it's close enough.
Yes, close enough. That's all what science is all about, right? Close enough, yeah? A round of applause for him. So the right answer is carbon negative initiative. Next up, representing the energy technologies area, please, ladies and gentlemen, welcome Jingbo Wang.
Imagine on a hot summer day, you take out your favorite can of soda from the fridge. That is the sound of happiness. Well, in science, it's actually the sound of CO2 leaving the water. We love CO2 when it's our drink, but we do not want too much CO2 in the atmosphere. You probably already know that. In less than 200 years, human activities have increased the CO2 level in the atmosphere by 50%, causing a global temperature to increase by at least 1.1 degrees Celsius. In order to avoid the negative impacts from global warming, we need to remove a huge amount of CO2 from the atmosphere, about 500 billion tons. So how much work are we looking at? Take the world's largest CO2 capture facility. We need to build 1 million of such plants just to offset CO2 emissions from human activities. And even more plants are needed if we want to bring down the CO2 level back to pre-industrial level. As you just learned from the trivia, here at Berkeley National Lab, scientists have formed a carbon negative initiative to work together on removing CO2 from the atmosphere. One approach is to find a sorbent that can pick up CO2 from the air. You can think of the sorbent as a special sponge that can absorb CO2. Like every other sponge, CO2 needs to be released before you can reuse the sorbent again. And usually heat is applied to release CO2 and regenerate the sorbent. In one cycle of capturing and releasing, 80% of the energy goes to sorbent regeneration by heat. If you recall the scale of CO2 capture we just talked about, that requires a lot of energy and money. Our research team is developing a cheaper and more energy efficient way to directly capture CO2 from the air without using heat. It's a three-step process. First, we start with a liquid sorbent, which is a base solution that can selectively react with and trap CO2 in the solution. In the second step, we zap the solution with electricity. which triggers electrochemical reactions. In this process, our solution turns to acid and CO2 is released. Then we can collect a concentrated stream of CO2, either sent to deep underground for storage or use it to make other products like soda and even fuels. In the third step, we turn the acid solution back to base by using the byproducts from the second step. Now it's ready to use for the next capture cycle. By only using renewable electricity instead of heat as the energy input, our process can bring down the cost to capture 1 ton of CO2 from $600 to only $100. In the near future, your favorite can of soda might be made of CO2 directly captured from the air with our technology.
It's a very sad time, folk. It's the last trivia question. Are you all really disappointed? No? Neither am I, to be honest. But before we do that, you know, there's a lot of you here. So yeah, actually big up to everyone actually who came out today. So congratulate yourselves. So yeah, okay. Round of applause for yourselves. Well done. But we also want to say there's a lot of people online. So I think we peaked at almost 150, 200 people online. So I want to say hello to everyone who's tuning in from online at streaming.lbl.gov. So hi, everyone online. So everyone here, can you applause the people that are tuning in online? And just a reminder, those of you online as well will have a chance to vote. So you will also have a say in the People's Choice Awards. So, okay, almost trivia time. Did you want to practice any of your stand-up?
Yes, you remember I told you I'm trying to build a career in stand-up science comedian. I want to be a stand-up comedian, but for science, right? So last night, I prepared 75 new jokes I'm about to tell. Are you guys ready to hear them? Okay. One of them is, and here's the deal. If it's funny, I'm going to tell a joke now, okay? And if it's funny, just say, don't laugh. Just say LOL. And if it's not funny, just say OMG. Okay? Is that funny?
You're getting it right.
Thank you. Yeah. Is that funny? Okay. I'm not going to give out my jokes. Sinead, over to you.
Okay, right. Last trivia question, folk. Okay, the technique of comparing the abundance ratio of radioactive isotopes to a reference isotope to determine the age of a material is called what? We all learned this in school, right? Last trivia question. I think he's disqualified.
Okay, go ahead.
Carbon dating?
Carbon dating or radioactive dating, aka dating in the Bay Area, is right.
Correct. Round of applause for the head's lavish gift.
It's okay, it's nearly the end. You don't have to put up with me for much longer. Right. Last but not least, from biosciences, it's Ying Wing.
We all have our favorite food, and we choose what to eat depending on our situation. For example, what you eat at home alone is probably quite different from what you'd prefer at a buffet with some friends. And this is also true for the microbes. Microbes can eat a wide variety of carbon molecules and have their preferences. Historically, research on microbial food preferences has focused on only very narrow and isolated cases. For example, examining a single microbe in a culture tube with 1 or 2 simple foods. However, recent research has shown that there is a buffet of diverse carbon molecules in the soil. So, how would a microbe alter its diet when having access to that variety of foods? Just imagine, if you were at a buffet, would you still choose to only eat that pizza? Or what would happen in a soil community where there are many microbes with similar food preferences? Would they compete or share food with each other? Studying these more complex scenarios is challenging, but has a potential to help us increase the sequestration of carbon dioxide from the air into the soil, so to help us tackle the climate crisis. And this is where my research aims to contribute. I study food preferences of soil microbes using mass spectrometry, which can identify and quantify a great diversity of carbon molecules in complex samples, so that I can track which molecules the microbes like to eat and to produce at a carbon buffet in the soil. Soil contains more carbon than in the atmosphere and all plants combined. When plants take up carbon dioxide for photosynthesis, they can release a great portion of that carbon into the soil containing diverse molecules. And there, lots of microbes look at this feast and decide what they like to eat. Some prefer the carbon that is easier to digest, so this carbon will be respired back to the atmosphere. Some other microbes, however, may prefer the carbon that is better at helping them to build their bodies, so this carbon will be more converted to microbial biomass or other products that could potentially stay in the soil longer. And my goal is to identify which microbes like to eat which carbon molecules at the soil buffet, and how the different microbes can eat as a team to efficiently store more carbon in the soil with lowered carbon dioxide emissions, and therefore to help mitigate climate change.
Thank you very much. Thank you. That was fantastic. You all made it. A round of applause, a round of applause, a round of applause. Thank you very much. The audience, please stick around for some important information. But first, let's call all our distinguished finalists back on stage.
Woo!
Give them a massive round of applause.
That's everyone. So one more round of applause. And take a bow.
Take a bow.
Okay, so now you have to get to work. So while the judges are deciding who the winner is, you also have a chance to vote for your favorite. Please rip off the coupon at the back of the brochure and make sure to put it in the next 10 minutes. Those of you online, there's the online survey. You can do the same thing. So get them back in as soon as possible because we do need to have them calculated. You don't want to miss your vote. We'll be back here at 4:50. Don't be late. 4:50 to announce the winner. But in the meantime, enjoy yourselves. We have some snacks and refreshments on the right-hand side, and we have our lab's very own DJ Miles Green to put up some tunes for the next little while. So thank you all. See you back here 4:50. Don't be late.
Thank you very much. We are back.
We're back.
Are we ready?
You got 10 seconds to get back here. You're going to miss the winners.
To get back.
To
hear.
No, I guess there's not very many people who know countdown.
Yes.
All right.
Yes. Before we go to what you've all been waiting for, I want to give a special thank you to DJ Miles, the voice of Berkeley Lab, the AV Wizardry. Make some noise for DJ Miles Green.
Thank you. Thank you. Thank you. Appreciate that.
Okay, and there's another person that we're actually gonna get you all to sing. Aren't you delighted about that? Yeah, I'm never doing this again. So there's a very special guest online right now, and that is Director Witherell, and it is also his birthday today. So we are going to attempt to sing happy birthday to Director Witherell. And honestly, I'm not that optimistic about how well we're going to do it. But let's try, right? Okay, so are we ready? Everyone's here? Yes, yes. Okay. Everyone's ready? Yeah? Everyone's ready? Okay. One, two, three. Happy birthday to you. Happy birthday to you. Happy birthday, Director Witherell.
Happy birthday to you.
Happy birthday, Mike. You're the best. We love you.
You've almost redeemed yourselves for not knowing that dark matter makes up 85% of the mass of the universe. Almost. Okay. So we've got a lot of people to thank. You can imagine this is a lot of work, and we're going to take our time thanking people. So do you want to start?
Yes. I'm gonna call Mike on stage.
The screen. Let's do these first.
Yes.
Yeah.
So we want to give a special thanks to everyone who has contributed to the success of this, and special thanks to the audience for hanging in there and logging in your votes. And to our esteemed judges, panel of judges, we appreciate you for making it all the way. Thank you, thank you, thank you very much. A round of applause for all our judges, please.
Okay, you just saw the cream of the crop today, the finalists, but there are actually a lot more people who applied, and there were screening judges. So I want to thank all the screening judges that are on the slide right now. So Anne, Bashir, Jen, Lauren, Lydia, Peng, Ray, Rajiv, Tom, Yang, and Yi. Thank you all very much for doing the first bit of work and selecting the finalists. Okay, a lot of organization. So obviously our AV audio people, Miles and Darren, big thank you. We've already given a bit of a... the comms team, the art and video productions team, thank you all for helping us make it such a great production. And last but not least, the Career Pathways Office, especially...
Round of applause, please.
Yeah,
thank
huge
you.
round of applause.
Thank you. Thank you.
Meg, Justin, and Stephanie, every year I think it gets better, and it's all down to you guys. So thank you so much. So I think we're going to bring you all up on stage right now. So you're going to do a 3-minute slam. Surprise. But can we call Meg, Stephanie, and Justin up on stage right now to say thank you?
So may I please call on Riva, Rajiv, Lydia, and Ryan, 2020 and 2019 Slam champions, to come and present something special to these wonderful, special people. Okay.
Oh, I got something.
Yes. Round of applause, please. Round of applause. Give it to her. Yes. Yes. Can we take some pictures? Yes.
I'm not prepared. I'm sorry.
Yes. On behalf of...
That's right. That's right.
Thank you very much. On behalf of all the postdocs and also all the SLAM alumni, we want to say thank you to all these wonderful people.
Okay, it's time.
What
So-
you've been waiting for.
You have the winners ready, I believe. So I bring up Carol Burns, our Director of Research, to announce the winners.
Round of applause for her, please.
So thanks everybody for hanging in. Let me say at the outset that for sure everybody is a winner. That's a bit of a I know we say that every year, but having judged last year and this year, I can say this year was really hard. And we all of the judges had a favorite person or two who didn't end up in the top 3. So you all can be incredibly proud of your efforts. So I think we start with the People's Choice. All right, our People's Choice winner is Ying Wing from Biosciences, finding microbes' favorite food.
Ying Wing from Biosciences. Round of applause for her. Stand up for pictures. Yeah.
Congratulations.
Congratulations.
Thank you so much. Thank you, Meg.
All right, now we get to our top 3 that will be going on to the Bay Area SLAM.
And I'm going to say, we have to say beat Livermore because they said that with me there. They said
Oh
beat
my
Berkeley.
God, Meg just said when she saw the Livermore competition this week, They said beat Berkeley. Them's fighting words. Them's fighting words, gang. All right, the stakes just went up. In third place, Aparajitha Srinivasan, Biosciences, choosing the right road to aroma.
Round of applause. Congratulations. Wonderful.
All right, in second place, Mohammed Ombadi, Earth and Environmental Sciences, like father, like son.
Congratulations.
Thank you. All right. Okay.
Congratulations, Mohammed. Round of applause.
All right. And in first place, this year's winner of the Berkeley Lab SLAM.
Drum rolls.
Ready? Sarah Gleeson, Energy Sciences.
Congratulations. Congratulations, Sarah. Wonderful. Good job.
With that, let me turn it over to Meg to say farewell.
Oh, I'm blocking the camera. Hi, everybody. I'm going to pass it back to the pros because I've got nothing except for just eat a lot. I got a lot. Eat a lot. Okay? All right, great.
I want to say something as well.
Okay. Do you want to go first? Okay.
Thank you very much, everyone. I just want to give a vote of thanks and a special thanks. This is a surprise because she doesn't even know I'm going to say this. I want to give a special thanks to Sinead Griffin. Sinead has been really special to me because she's been instrumental to my science communication career. She coached me when I was going to represent Berkeley Lab in Capitol Hill in Washington, D.C. She was literally my coach. The lab hired her to coach me. So I want to say thank you very much to Sinead, and we wish her happy retirement, but not from the lab. She's retiring from the SLAM, hosting the SLAM. So happy retirement from emceeing the SLAM. A round of applause for Sinead, please.
Thanks, Bashir, and thanks for being my MC squared. Said it again. Oh, gosh, yeah. Last time I can do that one, I guess. Okay, right. There's one more important announcement to make. Oh, by the way, Energy Sciences Area 1 again. Aren't we delighted? Okay. The bribes worked, folks. We have one more announcement, and that is that the winners of the Berkeley Lab SLAM will represent us in the Bay Area SLAM. So they will battle it off on October 20th. I got the date right, Meg? Yep. October 20th at 3 p.m. And they will be battling against Livermore, Sandia. Good. Well done, everyone. SLAC and LVL. So we wish them all the best. We know you're going to win. Don't worry about it. No pressure, but represent us well. Listen, folks, it's been great. And we'll see you I won't see you next year. I'll be on the other side. But see you all next year. And congratulations to everyone and to the winners.